Imagine a factory that doesn't build cars, doesn't build phones, and doesn't build anything you can hold in your hand. Instead, it builds something invisible. Intelligence itself, packaged into silicon, produced at a scale nobody in the history of manufacturing has ever attempted. Now imagine that this factory isn't owned by a chip maker. It's owned by a company you already know for something completely different. We're not talking about a car company anymore. We're talking about a company trying to mass produce artificial minds. So what happens when the world's most talked about EV maker decides that its next real product isn't a car at all? What does it actually take in raw computing power to give a humanoid robot something close to common sense? And why would a company that made its name building electric sedans suddenly need enough chip capacity to rival the entire data center industry? Stick around, because by the end of this video, you'll understand exactly why the next chapter of this company's story might have nothing to do with what's parked in your driveway. Before we go any further, make sure you're subscribed to Tesla Tech so you never miss videos like this. We break down what's really happening inside this company. No hype, no fanboy spin, just the numbers and the engineering. Company background. Let's set the stage first, because this story only makes sense once you understand where this company actually stands today. Tesla built its reputation on electric vehicles, and it still sells more EVs in the United States than any other manufacturer, with well over 1 million vehicles delivered globally last year alone. Its gigafactories in Texas, Nevada, California, Berlin, and Shanghai form one of the largest manufacturing footprints of any automaker on the planet. But here's the thing, Tesla has never really described itself as just a car company. For years now, the company has quietly repositioned itself as an artificial intelligence and robotics company that happens to sell vehicles as its main revenue stream. Elon Musk has said this openly on multiple earnings calls. And if you look at where Tesla is spending its engineering talent, that description is starting to look less like marketing language and more like an accurate summary. Why does that matter for this video? Because the same neural network stack that lets a Tesla drive itself down a highway is now being repurposed to teach a two-legged robot how to walk through a warehouse. Pick up a tool and hand it to a human being. And that robot, Optimus, has quietly become one of the most ambitious, most expensive, and most computationally demanding projects the company has ever attempted. Introducing the new chapter, Optimus and the AI-5 chip. So let's talk about what's actually new here. For the last couple of years, most of the Optimus conversation has centered on the robot's body. Its joints, its hands, its balance, its ability to walk without falling over. That's the visible, easy-to-film part of the project. But according to Musk, the harder problem was never the body. It's the brain. And that's where a new chip called AI-5 enters the picture. Musk has publicly stated that roughly a quarter of the output from Tesla's next-generation chip infrastructure, something the company has referred to internally as its terafab compute strategy, could eventually be earmarked specifically for powering Optimus units. Based on rough math, using the AI-5 chip as the baseline, that allocation could theoretically support somewhere in the neighborhood of 1 billion Optimus-class brains per year, and around 250 gigawatts of dedicated AI computing capacity annually. Now, before your eyebrows shoot up, that is not Tesla promising to build 1 billion physical robots. Nobody is claiming that. It's a scale calculation, a way of illustrating just how much computing infrastructure this vision would require if it were ever pushed to its theoretical limit. But even used as a thought experiment, the number tells you something important. Tesla isn't thinking about Optimus as a side project anymore. It's thinking about it as an entirely new category of product that needs its own dedicated semiconductor supply chain. So the real question becomes, why would a walking, talking humanoid robot need anywhere near that much computing power in the first place? Design details. Why a robot needs a supercomputer for a brain. Here's where it gets genuinely interesting, and where a lot of people underestimate just how different this problem is from building, say, a factory arm that welds car doors. A traditional industrial robot is dumb by design, and that's not an insult, it's a feature. It repeats the same motion, or in the same location, on the same object, thousands of times a day. Its computing needs are predictable because its job never changes. Optimus was never designed to work like that. Tesla's stated goal is a robot that can walk into an unfamiliar room, recognize objects it has never seen before, understand spoken instructions, pick up something fragile without crushing it, and course correct the moment something unexpected happens. A person walking into its path, an object slipping from its grip, a surface that isn't quite where it expected. Every one of those capabilities adds another layer of computational demand on top of the last one. A robot that can only recognize a coffee mug is one problem. A robot that can recognize the mug, judge how full it is, calculate the right amount of grip pressure, track a person's hand reaching toward the same mug, and adjust its movement in real time. That's a completely different order of complexity, and it all has to happen in a fraction of a second. using onboard hardware, not a data center sitting somewhere on the other side of the country. That's really the design philosophy behind AI5. It's not simply make the chip faster. It's give the robot enough spare computational capacity that it doesn't fall apart the moment reality stops behaving predictably. Power, compute, and the powertrain of a robotic brain. If Optimus were a car, this is the part of the video where we talk about the battery pack and the motor. For a humanoid robot, the equivalent conversation is about power draw and processing throughput, because ultimately, that combination determines how long the robot can operate and how much thinking it can do while it works. Based on figures currently being discussed around the AI5 chip, Tesla is targeting roughly 2,500 trillion operations per second of processing capability, a significant jump from the 100 to 150 trillion operations per second offered by the current generation Tesla AI chip used in vehicles and earlier Optimus prototypes. The chip is also said to carry around 192 gigabytes of onboard memory, with data transfer speeds reaching as high as 1.5 terabytes per second. Now, it's worth being upfront here. These are Tesla's projected figures. Not independently verified production benchmarks and final specifications on shipping hardware could shift before mass production begins. But directionally, the jump is enormous, roughly on the order of a 15 to 20-fold increase in raw processing capability over the current generation. On the power side, Tesla's working estimate suggests each Optimus unit could draw up to 800 watts of power under peak computational load. If you scale that across a hypothetical fleet of 10 million robots, the theoretical peak demand would be somewhere around 8 gigawatts. Although in practice, robots wouldn't all be running at maximum computational load simultaneously, so real-world demand would sit well below that ceiling. Still, it's a useful number because it exposes something people rarely think about with robotics. A fleet of intelligent machines isn't just a manufacturing challenge, it's an energy infrastructure challenge, similar in scale to powering a small city. Range and uptime. How long can the brain actually think? For an EV, we'd usually talk about range and charging speed here. For Optimus, the equivalent question is uptime. How long can the robot operate, and how much of its computing budget goes towards simply staying balanced and aware versus actually doing useful work? This is where the AI5 chip's efficiency claims matter more than its raw horsepower numbers. Tesla has suggested that AI5 could eventually deliver up to 50 times the performance of the current AI4 chip, while costing around a tenth of what comparable NVIDIA data center hardware costs. Again, that's Tesla's own claim target, not a confirmed third-party verified figure, so it deserves a healthy dose of skepticism until real production units are benchmarked independently. But if Tesla gets even reasonably close to that efficiency target, the implications are significant. It would mean Optimus could dedicate more of its power budget to actual task processing rather than burning energy just to stay balanced and oriented. Practically speaking, that could translate into longer operating windows between charges, faster reaction times in unpredictable situations, and the ability to run more sophisticated perception models without needing a bigger, heavier battery pack strapped to its back. How does this compare to the competition? Tesla is far from the only company chasing this. Let's go through the field because context matters here. Boston Dynamics, with its Atlas Humanoid, has arguably the most impressive raw athletic performance of any robot shown publicly. Backflips, complex parkour-style movement, and years of engineering pedigree behind it. What Boston Dynamics has historically lacked is Tesla's manufacturing scale and vertically integrated chip strategy. Atlas has largely been a research and demonstration platform rather than a mass production consumer or industrial product. Figure AI, backed by major names and tech investment, has been moving fast with its Figure 02 and newer models, and has already run pilot deployments inside real warehouse environments with commercial partners. Figure's strength is speed of iteration and strong AI partnerships, though it doesn't yet have anything close to Tesla's in-house chip fabrication ambitions. Unitree, the Chinese robotics company, has taken a very different approach, undercutting everyone on price. Unitree's humanoid platforms have been sold at price points dramatically lower than Western competitors, which has made them popular for research labs and smaller companies, even if their capability set is generally considered less advanced than Optimus or Atlas. Agility Robotics, maker of Digit, has quietly become one of the more commercially mature players, with robots already working inside real warehouses, moving totes and packages for logistics clients. Digit isn't trying to be a general-purpose household robot. It's laser-focused on warehouse work, and that focus has helped it get to real paying deployments faster than some flashier competitors. So where does that leave Tesla? Tesla's advantage isn't necessarily that Optimus is the most physically capable robot today. By most independent assessments, it currently is not. Tesla's advantage is manufacturing scale, vertical integration from chip to battery to factory floor, and Musk's willingness to commit enormous capital toward custom silicon rather than depending on third-party chip suppliers like NVIDIA, the way most competitors currently do. Whether that bet pays off depends entirely on execution, which brings us to the next section. Long-term strategy. Where is this actually going? Musk's stated long-term vision positions Optimus as potentially the single largest product line Tesla has ever built, bigger in his framing than the entire vehicle business. That's a bold claim, and it should be treated as exactly that, a claim, not a guarantee. The recent milestone that's fueling renewed attention is the tape-out of the AI5 chip. For anyone unfamiliar with chip terminology, tape-out means the chip's design has been finalized to the point where it can be sent off for physical manufacturing. It's a meaningful transition from concept on a whiteboard to actual silicon being fabricated. Samsung's foundry has reportedly been lined up to produce AI5 at its Taylor, Texas facility, using a 2-nanometer class manufacturing process, which is among the most advanced chip fabrication technology available anywhere in the world today. Mass production is still a separate milestone from tape-out, and there's typically a gap of many months, sometimes longer, between a chip design being finalized and it shipping in volume inside real products. But the fact that Tesla has moved AI5 out of the conceptual stage and into actual fabrication planning signals that the company is treating this as a near-term priority, not a distant moonshot. Looking 2 to 5 years out, the stated ambition is for Optimus production to scale into the hundreds of thousands and eventually millions of units annually, with the robot deployed first inside Tesla's own factories, then gradually into external industrial and eventually consumer settings. Whether that timeline holds is very much an open question, and Tesla's track record on self-imposed deadlines, from full self-driving timelines to the original Cybertruck launch, suggests a healthy amount of patience is warranted here. Challenges, risks, and honest limitations. Now, let's be fair and balanced about this, because there's a lot that could go wrong. First, the chip production numbers being discussed: 1 billion AI brains a year, 250 gigawatts of dedicated compute capacity, are based on theoretical maximums, not committed production plans. Semiconductor fabrication at that scale would require an almost unprecedented build-out of foundry capacity, energy infrastructure, and supply chain coordination. Even the biggest chip manufacturers in the world today don't operate at anywhere near that scale for a single customer's product line. Second, mass producing a humanoid robot is an entirely different manufacturing challenge than mass producing a car. Every unit needs a processor, memory, power delivery systems, thermal management, sensors, actuators, and precision mechanical components, all of which need to come together in a form factor small and light enough to be carried around on 2 legs. If chip production scales faster than actuator or battery production, or vice versa, the mismatch becomes a bottleneck regardless of how good the AI5 chip turns out to be. Third, safety and regulation remain enormous open questions, especially for any application involving robots working directly around humans, let alone the surgical scenario sometimes used as a stress test example for computational demand. To be absolutely clear, nobody, including Tesla, is suggesting Optimus is currently capable of performing autonomous surgery. That kind of example is used purely to illustrate how much simultaneous sensory processing, prediction, and precise motor control a genuinely capable physical AI system would need, not as a near-term product roadmap. Real-world deployment in anything safety critical would require years of validation, regulatory approval, and reliability testing that simply hasn't happened yet. Fourth, cost claims deserve scrutiny. The idea that AI5 could deliver 50 times the performance of AI4 at roughly 1/10 the cost of comparable NVIDIA hardware is, right now, a target Tesla has stated publicly, not a number verified by outside benchmarking. NVIDIA's dominance in AI compute isn't an accident. The company's data center division alone generated approximately $75.2 billion in quarterly revenue recently, up 92% year over year, built on genuinely difficult to replicate manufacturing relationships and software ecosystems. Unseating that position, even partially, would be a massive undertaking. Final analysis. So where does all of this actually leave us? Tesla is making a bet that the future of robotics isn't primarily a mechanical engineering problem, it's a computing problem. The company already has real experience building custom AI silicon, real manufacturing scale, and a public willingness to spend enormous amounts of capital chasing long-term infrastructure bets, from gigafactories to its Dojo supercomputer efforts to now terafab-style chip production. At the same time, the gap between chip taped out and millions of robots working in the real world is enormous, and history has shown that Tesla's own timelines tend to be optimistic. The competitive field is also far from empty. Boston Dynamics, Figure AI, Unitree, Aptronic, and Agility Robotics are all making real progress, some of them already deploying robots commercially today, while Optimus is still largely in development and limited internal use. What does seem clear is this: whether or not Tesla hits 1 billion AI brains a year, the direction of the industry is shifting toward pushing artificial intelligence out of centralized data centers and directly into physical machines that can see, decide, and act in the real world. Optimus, AI5, and Tesla's broader compute strategy are a very visible, very ambitious bet on that shift actually happening, and how it plays out over the next few years could say a lot about where robotics as a whole is headed. That's the full picture on Tesla's AI5 chip and what it means for the future of Optimus. The ambition, the numbers, and the very real questions that still need answers before any of this becomes everyday reality. If you found this breakdown useful, hit like, drop your thoughts in the comments. Do you think Tesla can actually pull this off, or is this getting ahead of itself? And make sure you're subscribed to Tesla Tech with notifications turned on, because we'll be covering every update on AI5, Optimus, and everything else coming out of this company as it happens. Thanks for watching, and we'll see you in the next one.